Do you know the difference between raster and vector files? This overview will help you differentiate for an improved design workflow. With so many images to choose from, it can be overwhelming to determine which file formats to begin with. Do you use raster or vector images? Raster images are made up of pixels, while vector images are formed by mathematical curves and paths. Being comfortable with the ins and outs of both formats and how they translate when exported is an essential skill for every designer. Let's start off by looking at raster images. Raster, or bitmap images, consist of tiny squares called pixels. These pixels contain bits of color and, when combined, they build images. The more pixels in an image, the higher the quality, and vice versa. When you zoom in on an image, the pixels become more apparent, while the details of the image become blurry. Notice how the edges of the eagle ray become pixelated and jagged when magnified. This is a key indicator of a raster-based image. Pixels are the smallest unit of measurement in a raster file, and they are the basis of resolution in a raster file. How you can use a given raster image depends on its size and quality. Quality is often dictated by how many pixels are contained in an inch. This is expressed as pixels per inch, or PPI, or sometimes referred to as dots per inch, or DPI, as well as the overall dimensions of the image, which is also expressed as pixels. For example, an image may be 5,000 pixels wide by 2,500 pixels high. Hardware, or the screen resolution, is equivalent to a display's vertical pixel count times the horizontal pixel count. Resolution density is measured in pixels per inch. In other words, resolution density measures how many pixels will fit within 1 inch of printed space. The greater the PPI and dimensional measurements, the higher the quality. Let's take a look at a raster image. This is the image displayed at 100%. Here I've zoomed in to 400%, and finally at 3,200%. As you can see, as we increase the zoom value, we start to see the pixels, and the image becomes less clear and crisp. This is the same page at different views. Notice that the original file data stays the same. The image size and the dimensions are identical. So are the width and the height. The only thing that's different here is we're viewing the screen differently. Here I'm zoomed out to 12.5%, and here I'm viewing the same image at 100%. The Photoshop image size dialog box looks like this. It gives us a lot of information about the image. It will tell us what the image dimensions are. This is the image's native dimensions, and in this case, they're 2,886 wide by 2,160 pixels tall. This is based on a pixel density of 72 PPI. If we multiply the number of pixels in the width by the number of pixels in the height, we'll end up with the total pixels for the image. As this number increases, the file size will also increase. The more pixels, the more data the image contains. Digital displays use a screen resolution of 72 PPI. That's because it's the maximum number of pixels that a screen can physically display per unit of area. Notice here that the Resample checkbox is deselected. This will constrain the resolution to the print dimensions of the file so that no file data is lost or distorted. That means that I can change the width and the height or the resolution, and the numbers will reconfigure, but I'm not actually getting rid of or adding any additional information. As you can see here, the original image size is 17.8 megabytes. The pixel dimensions are the same in each of these screen grabs. All I've done is simply change the resolution, which in turn will change the width and the height of the image. So what we're doing here is we're doubling the PPI, but the print size will inversely decrease by half. Here we're doing the same thing, but instead of using 150, I'm using 300 for the resolution. And you can see that the physical size decreases by half based on the new resolution. Once again, the amount of pixels is not changing at all. This method of editing an image is called non-destructive resolution scaling because no pixel data is lost in the physical image dimensions. If we go ahead and check the resample dialog box, we'll increase the resolution, and what happens is we're going to artificially add pixel data where it did not really exist, thus making a giant and poor quality image. We refer to this as oversampling. It's kind of like stretching a spring too far. It will never go back to its original shape and integrity. Once we stretch our spring out, or we artificially inflate or change the pixel data in an image, we're going to have missing data. Alternatively, we can downsample an image and reduce the dimensions and file size. This does not cause as many problems as upsampling. Once again, if we leave resample checked, when we make a change to the width and the height, the resolution will remain, and our file size is going to decrease and get smaller. What happens is we're throwing away a lot of the pixel data and making the dimensions smaller. Applications such as Photoshop are much more successful in downsampling images rather than upsampling images. The next thing to consider with raster images is a bit. Bit is something that affects file size and properties. A bit is a binary decision. It's the smallest unit of measure for a digital file. You can think of it as a switch that can either be set to being on or off. Here's an example of a 1-bit file. Notice that it only has two values, black and white. It almost looks like a pointillistic painting. You can think of 1-bit files as the presence of full light or the complete absence of light. If we go ahead and change the bit to 2 bits, we can have 4 values per channel. And as you can see, we'll recover a little bit more data in our image. Here's an example of a 3-bit file. This is giving us 8 values per channel. With 4 bits, we get 16 values per channel. And as we increase the bit depth, and in turn the values per channel, you can see that we start to recover more of the data that was in the original image. Here's what the image looks like as a 5-bit file. It now contains 32 values per channel. And at 6-bit, we get 64 values per channel. 7-bit gives us 128 values per channel, and 8-bit will give us 256 values per channel. So what's a channel? Well, channels are grayscale images that store different types of information. They're all part of the same original image. We don't normally see them, they just exist as part of the image. Standard device outputs typically don't exceed 8 bits or 256 possible values per channel, so we're going to focus on those. When we're speaking about digital images, we have 3 color components, red, green, and blue. When we combine these together, we'll get the final color. RGB images have channels for each color, red, green, and blue. Plus, they contain a composite channel, which is used for editing the image. The color information channels are created automatically when you open a new image. The image's color mode determines the number of color channels. In standard RGB color, each channel has 8 bits, or 256 possible tones. When we add the RGB possibilities together, we end up with millions of possibilities in regards to the actual color. Some images also have alpha channels. Alpha channels store selections as grayscale images, and you can add alpha channels to create and store masks, which let you manipulate or protect parts of the image. In this example, I've created an alpha layer mask that is only revealing the harbor seal image in the shape of the seal. The rest of the information in my image is now transparent. If we simply turn on the layer mask and turn off all the other channels, we'll see a black and white representation of what the mask looks like. When we're working with alpha masks, we say that white reveals and black conceals. You'll often need to compress images. File sizes can get very large based on things like resolution, the physical size, the bit depth, etc. And depending on how we're delivering the information, we'll often need to make the images smaller. Here I'll be talking about compression with the JPEG file format. Here is an image, and it originally was 1000 pixels by 400. This image right here is saved with no JPEG compression. The file size is 381 kilobytes. Here's the exact same file, but I've saved it with maximum JPEG compression. The file size is reduced down to 35 kilobytes. Now, in theory, that might sound great, but when we look a little bit closer, you'll see that the lower quality or more compressed version of the image starts to lose details. When we compress with JPEG, we'll end up with something called artifacts. Artifacts are the little bits of information where interpolation occurs. This is very apparent around the edges of the harbor seal. You can see how the image looks blurry and a little bit dirty and muted. When a file is compressed as a JPEG, it throws away data. It creates holes where pixels once were. When the file is opened, the application takes an educated guess about how to create the missing pixels based on surrounding values. Applications like Photoshop allow us to find the best balance between quality and reasonable file size. This is the Photoshop Save for the Web dialog box, which allows us to compare the original image with different examples of how various compression settings will affect the image, both in the visual quality and in the file size. Now let's switch back to vectors. Vectors use a different approach to image rendering. They're made up of paths and curves that are dictated by mathematical formulas. These paths and curves are produced exclusively through design software that's used for creating vectors. This would be something like Adobe Illustrator or Sketch. Due to their algorithmic makeup, vectors are infinitely scalable, and they'll remain smooth and crisp even when sized up to massive dimensions. As you can see, this fish image remains smooth and intact even when I zoom in. Elements like fonts render the same way. When they're sized up or down, they retain their quality. Raster images are used in many situations, but they're not the best for every instance. Learning to know when to use raster and when to use vector in specific applications is essential for every creative. Since raster graphics are made up of square-shaped pixels, they're best for displaying detailed photographs and subtle gradations in color. Because raster images are more readily available in various file formats, they're more accessible and easier to view online. The accessibility of these graphics makes them more shareable online in multiple applications, especially on social media and through web image browsers. While raster graphics are nice for showcasing detailed photographs and shareable images, they do not scale well. If you enlarge a pixel-based photo online, you'll start to see heavy pixelization, which can appear unprofessional to the end viewer. In addition, raster images can have large file size, dependent on the amount of detail that the image has. When you open up a large raster image, you'll notice the hefty file size in comparison to a smaller sized raster image. Knowing how to best optimize the quality of your graphic while keeping its file size low is a crucial skill for every creative. On the other hand, vector graphics have their own uses. Because vectors are made up of mathematical equations, they're infinitely scalable and are ideal for things like logos, geometric designs, and typography. Vector graphics also take up significantly less file space than their raster counterparts. While vectors are ideal for scalable logos, typography, and design, they're not ideal when displaying photographic images. Rather than being comprised of square-shaped pixels, vectors are made up of mathematical curves and lines, meaning vectors display visual information differently than raster images. So why does this really matter? Well, it's important to understand the differences between these two file formats so you can choose the best format for the artwork that you want to display and work with.